Commutator Flashback Friday. Remember all those exercises with commutator identities in Chapter 3 and angular momentum commutators back in Chapter 4? Well, guess what? They're back. Welcome, everyone. Today, we dive deep into the vector operator selection rules for rotation and see how those fundamental commutators shape quantum transitions. Let's get started. So the goal for problem 6.22 is to show that the commutation relations equation 6.50 to 6.54 follow from the definition of a vector operator, equation 6.33. And if you did problem 6.19, which I did not have scheduled, you already derived one of these. And then in part B, we want to derive equation 6.57. Okay, so we got a lot going on. Why do we care? Clearly, these give us the selection rules, which we can clearly see a nice need for in determining these things because I don't feel like doing 1,000 integrals when we could use some clever math. That being said, we know that these selection rules via the Wigner-Eckhart theorem gave us a combination of matrix elements or reduced matrix elements with scalar coefficients. So the challenge for this video is review the 𝐲𝐻-Gordon coefficients because they tie into these vector operators in angular momentum, as you probably could have been at forecasting based on what we did in chapter 4 and how angular momentum keeps playing a big role here. So go check those out, see how it is, and get ready to see those again because those direct products that are listed in the tables will come back and they will be very vital for us. That being said, this problem is not that tedious. Well, it's more tedious than it is anything else, but there's a lot of dynamic parts because we have 5 things to prove in part A and another thing to prove in part B. So again, as a reminder, there's a free companion PDF to help you follow along, although it's pretty much the same as in the video, just a lot of grunt work. All you have to do is access it using the link below and you'll be good to go. And of course, if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. So without further ado, let's dive into this question. Okay, stop number 1 has to be just a game plan to tackle this thing. 5 parts in part A and another part for part B. Let's get all these equations on the board just so we can see what we're dealing with. Clearly here for part A1 and 2, we're dealing with the vector operator, or excuse me, the angular momentum operator LZ acting on the vector operator Z and plus minus, same plus or minus that we dealt with in chapter 4 for the angular momentum, which we'll revisit when we get there. And then we have the raising and lowering operators for angular momentum, all with the different operator types for the vector operators here. And we see we get a cascade of wonderful results that we can chug out pretty quick. But again, slightly tedious, so just be aware. 5 parts for A, 1 part for B, which is the selection rule criteria for VZ. Again, this is oriented all with the Z-axis. When you look at it in another textbook or other research papers, they will mark it as a tensor and just put an index there. So be aware, it does come back, and you will need to see this in a more fruitful light after you get done with this simple case. So be aware, it does get more complicated and really fast. But let's get started and let's see how we dive into these things, although it'll be nothing but tedious work, so let's start breezing through it now. Alright, so stop 1 of part A, we just have the commutator of LZ and VZ, which we can read off directly from equation 6.33, which tells us what the vector operator is with the commutator. So we have the I, H bar, epsilon, I, J, K, and so we see that we have here Z, which corresponds to the index number 3, and Z, which corresponds to index number 3. So you see we got a 3, 3 there. That's what that represents. And thus we have any leftover statement of K here, but this doesn't matter for any of the K values. It could be X, could be Y, it just doesn't matter because the 𝐕𝐢𝐝𝐿𝐼 here, this epsilon, gives us a 0 when we have repeated indices. So because of that 0, this holds for all k, and we're good to go. So that wraps up the first one pretty quickly, leading us straight to part 2 of A. And now you see we have to do a little more work here because we have LZ with the raising and lowering vector operator. Okay? And this, of course, can be discussed in the book as far as the derivation. But here's the formula for you just to keep in your tally book. And you see it has the same form of x plus or minus I, y. This has been used in the whole argument since chapter 3 and 4 and finding, or even with the harmonic oscillator, finding those algebraic solutions. A bunch of quote guess and check stuff that worked out pretty well based on a hunch. And then to deal with the fact that you have a plus or minus on the right hand side of the commutator, reference back to problem 3.14 where we showed the distributivity identities for commutators and things like that. So that being said, we use the right distributive law and split these up. Of course, the scalars can come outside. No big deal, just be aware. Now again, we have to apply the 6.33 with the 𝐕𝐲𝐝𝐿. And I told you back in chapter 3 or 4, whenever I first implemented this was going to come back and save you a lot of trouble later. Okay? The thing to note here is that 3, 2, 1 is called an even permutation. So again, if I take x, y, z, and I shuffle the arrangement, so I put x back here, put y back here, we see that we get z, x, y, which is an even permutation, which is what the 312 represents. So because it's even, we get a plus 1. Cool. This is 3, 2, 1. So if we start off with x, y, z, and we end up with a z, y, x, this doesn't occur naturally in some kind of cycle like this does. So this is called an odd permutation, and thus we get a negative 1. But because it is a permutation of distinct indices, we do get something in there that's not 0. Reference above if you want to see the 0 case. And this will be a heart in simplifying the rest of these commutators, so spending a little bit of time on it now will pay off later. But nonetheless, we plug in 1 and negative 1, and now it's just a simplifying match. So we get I and I here from the IH bar epsilon VK. Cool, but then the negative 1 and I squared. The double negatives cancel, so we're left finally with IH bar VY plus minus H bar VX. Of course, from here, we can factor out a plus or minus H bar. And the reason why we do this is because it's a plus sign on the Y. And the only way to get a plus sign there is to have a plus minus inside. Plus to plus gives us positive, negative to negative gives us positive, so that's the only way to assure that stays positive there when factoring out a plus or minus. And then we can reformulate this back into the raising and lowering operators, so we're good to go there. Alright, so those two are done. Let's get on to number 3 in this part. Wonderful, wonderful. So number 3, instead of just having the vector operator identity, we go back to equation 4.105, which is the raising and lowering operator for angular momentum. And now we get a twofold approach to this distributivity law. So let's start with the left-hand side here after we sub in these definitions. And we see that by using the left-hand distributive law, we get Lx here with Vx, Vy, plus or minus I, Ly, Vx, Vy, cool. Now we can break each of these into two commutator brackets each. And we see by doing so, we have to use curly brackets to keep them contained so that we can keep this plus or minus and this I distributed properly. That being said, once we distribute everything, we see we have 4 commutators, plus or minus I on this one, and then we have to distribute this I into this one, so we get an I squared there. Cool, no problem. From here, it's straightforward just to apply 6.33 with the 𝐕𝐲𝐝𝐿, so XX, we get a 1, 1, XY, we get a 1, 2, forcing the K to be 3. Here we get a YX, so we have a YX, and then the third one forces it to be index 3, so Z. And then we get to repeat it again with YY, so it's 2, 2. Naturally, we know that that's going to cancel because of the repeated index, so we get a 0, 0. We love that. Simplify away. Here, Of course, we had a +1 for even permutations. 1, 2, 3, 2, 3, 1. What else am I missing? 3, 1, 2. And then, of course, this is odd, so we get a -1. Fine. Again, we see we have an I, and -1. That cancels, or that will cancel out later, so let's just write it all down. I squared in this one as well, plus or minus. The plus or minus here gets flipped with this -1, so we have a minus plus. Of course, we have II here, H bar VZ, H bar VZ, opposite signs, and you cancel to 1, or cancel to 0, excuse me. And we like that. Nice little verification there. All right, moving on to part 4. In part 4, then, we only have the VZ part with the raising and lowering angular momentum. So again, we use the left-hand distributivity law. Then we factor, once we do that, then we push right into the 6.33, break that down with the vector operator rules with 𝐕𝐢𝐝𝐻𝐸 again. Again, you can start to see a pattern here. We get 1, 3, 2. That's not even, that's odd. We get 2, 3, 1. The 1 just gets bounced to the end, so we know it's even. So -1 plus 1, of course, the negative, let it go through. This plus 1 can be pushed here, so we're fine, but I squared from the distributivity gives us a -1, so we flip the minus or plus minus to a minus plus. And then if we factor that out again, we get this, again, be careful factoring out negative plus. We get the negative plus h bar with the same form of the vector raising and lowering operator. So we put that in, and we get problem of 4 or identity 4 done. Not a problem. Thus, we get to move on to the last identity in this sequence, which is angular momentum raising, lowering, and the vector operator lowering, raising. So again, we can take the form that we did for identity 3, put this in here with both of the distributive laws, and then simplify much like we did before, just with the opposite signage. Okay, so just be aware signs will change. Simplifying down with our curly brackets, because each one of these gets split out. So 2 things to distribute leads to 4 commutator brackets, so we're good there. Settle on through, distribute the I, change the signs if needed. This I squared goes to -1, so we switch this to a plus minus. And then, of course, XX, 1, 1, XY, 1, 2, YX, 2, 1, YY, 2, 2. And then, of course, if you have repeated, they go to 0, 0. If you have 1, 2, then you force the third index to be 3. That gives you a +1. 2, 1 forces the third index to be 3, so we get a Z with the -1. Nice little replication, a lot of practice. Not too bad once you have the first few down and you can just bully through them. You plug it all in, you see what the I's replicate with after this -1 flips this sign here, indicated in red. Both of these are I squared, so go ahead and flip the signs again. Plus, minus, and thus we get 2 plus or minuses for this combination of VZ. And this concludes the selection for the commutator selections in equation 6.50 to 6.54. Again, not too hard once you kind of see the scope. Very messy and kind of dynamics with just having to keep track of everything. So once you get the framework there, then you're good to go. But now that that's done, we can finally get on to something a little more cool, not just calculating, which is part B. And what we have to do is define the selection rule criteria stated in 5.7, I believe it was. And with this, we're going to follow the theme of the book, in which we sandwich or surround a commutator, and then we can see that we're surrounding them by 2 angular momentum eigenstates. With these commutator identities, we can now simplify it down and find the selection rules for angular momentum. So let's see how that's done. All right. So sandwiching these in between, again, we saw that LZ, VZ led that commutator relation. This one right here was equal to 0 in our chart, okay? That's fine, and this makes it real easy when we're sandwiching the 2 eigenstates of green and blue here on both sides of this relation. And when we have a 0 inside, again, we get a 0 right here from that. Love it, love it, love it. However, what we see here is that this commutator bracket can be written out in the commutator form, a hat b hat minus b hat a hat. So that's what we see here. Fair enough. But from here, we can quickly split this up thanks to linearity. So we get LZ over here, and then VZ over here. And here's where we're going to have to be careful. Here's where the ordering matters, because we know that the angular momentum operator of LZ on an eigenstate is an eigenvalue equation that we saw back in chapter 4 with the equation 4.118. So LZ here acting on some eigenstate of FML. That's a weird abbreviation. I can't believe I just caught that. And then we see that the operator yields an H bar M. Okay, so by applying with the commutator brackets leading to an LZ on the left hand side, we apply it to this state. With the other part of the commutator, LZ on the right hand side, we apply it to the right hand state. And we get the same state back because it's an eigenvalue equation, and NL and M are the eigenfunction. Cool, we can deal with that. But because we can put in an H bar M in it, we get an H bar M hat or M dash M prime from the left hand side, and we go back to the repeated state, but now we're just left with VZ as the operator. And here, when we apply LZ to the right hand side, we get an H bar M. And this, I hope the color coordinating helps you more than anything else, because you see that direction that they need to apply in. Very cool. And from this, we can quickly see that we could factor out these brackets, these Dirac notation inner product brackets. And once we do that, we right factor them. We're left with an H bar M prime minus H bar M. Factor out the H bar. You see that it cancels to 0 when you move it over to the other side. Awesome. And here's where we have to be careful in the statement of these things. We see that we have two options here, or three options really. Either M prime minus M could equal 0, the inner product brackets could equal 0, or they both can equal 0. However, when we're looking at guaranteed zeros, we know that this inner product has to be 0, right? Unless M equals M. M prime equals M, okay? Because if M prime equals M, then it doesn't matter what the inner product bracket is. That doesn't matter because M prime minus M will lead to 0, and everything times 0 is 0. Cool. However, if they're not equal, right, then we can say that this has to be 0, okay? And that brings us to that conclusion point of deriving equation 6.57, so we're good to go. Keep these with you. It really wasn't a hard question. It was a lot of work just to get it set up. Once you're in the setup, then you can repeat the same things we saw with the scalar operators and the parity operators, thankfully. And I will assume that this is going to come back in the next question. I'll have to double check. But nonetheless, we'll see how it all ties together here in chapter 11 later on in the book, so keep these in mind. So in summary, we got to see how the equations with the identities of the vector operators and all possible combinations of those operators are dealt with the commutation relations of the angular momentum, and thus the different types of selection rules that we can get from them, thankfully. Now, these selection rules, again, they're just kind of like, okay, these are cool facts. When are we going to use them? They will be used in a highly sophisticated manner here later in chapter 11 and in other parts of the perturbation theory. So be aware that they actually do have some context to them. And again, whenever we deal in the tensors in the next series of books, having this background will help very much. But, you know, none of this is possible without the supporters of this channel. So I have to give a massive thank you to all my supporters for making this possible. As always, I'm very grateful the fact that you have faith in this process, because it is a long, tedious, laborious process of love and care. So I appreciate your faith, especially with the conversations we're having about the style of education and how a lot of people are more into independent learning. I think this is a great avenue. But nonetheless, if you'd like to see more, you can always become a patron for access to supplemental material, current and future projects, and one-on-one help, which I have a feeling will spike up as the school year gets back to going. Right now in the summer, it's kind of chill. New content is posted weekly to help fuel your curiosity. I'm especially intrigued with the old giants of whose shoulders we're standing on and their work and how they gain their insightful wisdom, so to speak. So it's having that background is really fun. I love the article reviews. So if you have an article, please suggest it because I think that more will be better. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. And as always, thank you for watching. Until next time, stay curious.